coming. As Pete just said, fusion still offers enormous potential. Behind me is the only working fusion reactor that we have in our solar system. And I thought I'd be a bit provocative with the title of the talk to encourage you, and lo and behold, you're all here. I think what I want to point out here is there's a lot going on the surface of the sun. Notably, you can see a lot of sort of coronal mass ejections and these beautiful solar flares. There's enormously rich physics involved in that. What I'm going to show you next, these sort of images I'm sure you've all seen. This is a laboratory fusion plasma, so what we can do here on Earth. And you can see these sort of periodic eruptions, these bursts, these sort of hose lines of fuel which is coming out, very reminiscent of solar flares. They look more or less the same because they are. This is a very energetic, really energetic ball of gas which has turned into what we call the fourth state of matter, a plasma. And when you make a gas that energetic, it tends to wobble around a lot. And we see it on the sun, and we see it here in the laboratory. Now, what's interesting is if probably most of you would say the hottest place in the solar system is the center of the sun, actually, this is about 10 times hotter than the center of the sun, which sounds absurd. But I'll come to that as we go through the course of the talk. So I use this provocative title, How Do You Build a Star on Earth? So I've already given you one of the big challenges. To make fusion happen, to make the fuel react, you have to make it insanely hot, 10 times hotter than the center of the sun. Because the sun has gravity pulling everything together, which makes the reaction start. On Earth, of course, we can't have something the size of the sun sitting on Earth. So we have to think of a better way of building our stars on Earth. Now, I'm going to start with a quote from Eddington, and I found out 5 minutes before this lecture that Eddington actually came from Kendal, which is, you know, a good coincidence. I'm just going to read this verbatim. Eddington was the first person to hypothesize, at least correctly, where the sun gets its energy from, what powers the sun. This reservoir, and here he's talking about the power of the sun, can scarcely be other than the subatomic energy which exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. The store is well nigh inexhaustible if only it could be tapped. I love this quotation, nearly a century ago. I love this quotation because it sums up why I came to fusion, why all the people at my laboratory work on the subject, why it still offers enormous potential. Because it's well nigh inexhaustible if only it could be tapped. And we are every day working on how we tap that source of energy. So let's start with the basics. What is fusion? So essentially all you need to know is E equals mc squared, Einstein's very famous formula. So if we take deuterium and tritium, deuterium is heavy hydrogen, tritium is very heavy hydrogen, and we react them together. Now they're both positively charged, so they both repel one another. So to make them come together and fuse together, you have to make them very, very energetic. So that's why you need these enormous temperatures. So you get them very energetic, they come together, they'll join, they'll fuse, and as a byproduct, they'll produce helium and a neutron. Now, if you're good with mental arithmetic and you add up the masses of the two reactants, then take away the mass of the two products, you'll see that there's a significant residual mass. And that mass, if you put into E equals mc squared, gives you a lot of energy. So this is, as Pete said, exactly the opposite of fission, where you're taking heavy stuff and breaking it apart. With fusion, you're taking light stuff and forcing it together, but both give you energy. And in many ways, fusion is the ultimate energy source. It's clean, there's no carbon emission. It's unlimited fuel, effectively. We get these materials from seawater. We've got quite a lot of seawater. And lithium is very abundant in the Earth's crust. It's safe. Unlike fission, there's absolutely no risk of chain reactions. Look, I can tell you that I've spent all of my life trying to keep the reaction going. It's very easy to stop. And it's reliable in that it can run continuously. You're not waiting for the sun to shine and the wind to blow, so it can be part of the base load. It's also extremely high yield. If I burn energy at 20 kilowatt hours a day, which is a lot more than I do, even a lot more than your average American, Even working on that basis, the rest of my life, I could get from a bathtub of water and the lithium which is contained in 2 laptop batteries. So it's very high energy density, very high yield. So you need almost no fuel. Just a few grams of fuel is enough for the rest of your lives. You compare that with coal. I use my beautifully scientific unit of wheelbarrows. So the same amount of energy would be from about 1,600 wheelbarrows of coal. So you can see fusion is extremely high density. You don't need a lot of land to produce a lot of energy. So all of that sounds great. Clean, green, continuous, and no long-lived radioactive byproducts, and very high yield. So there's got to be a catch, and there is a big catch, but it's really, really hard. And what I said at the start, you have these like charges, they want to repel each other naturally. Go back to O-level chemistry, you know that like charges repel, so you need to get them very energetic to make them attract one another at the point that the strong nuclear force will take over. And this means that we need temperatures which are about 150 million degrees, about 10 times hotter than the center of the sun. Now, that sounds ridiculous. Of course, you can't just put that into a tank because it'll melt. So you need another way of holding the fuel at those temperatures. Now, you can do this because the fuel is charged, and you know that magnets will hold charged particles. So again, now back to O-level physics, you pass a current through this wire, through this coil of wire, and you see a magnetic field going perpendicular to the current, passing through that coil, and you can see the ion filings going around that coil. So there's a magnetic field there. So we can pass our charged particles down that coil. Now, with just a linear strip like that, they'll just leak out the ends. So what you do is you take that linear strip and wrap it round into a donut. And this is the machine that we use to make fusion happen here on Earth. So you see these big blue coils here. We're passing a current through those coils, which induce a magnetic field the long way around that donut or torus. And the charged particles will just whiz around following that magnetic field. Now that works pretty well. It's not perfect. It's not perfectly confining for some complicated physics reasons. And so you actually need to have a slight twist on the magnetic field. You need it slightly helical. And we do that by putting a transformer down the middle of the machine. We pass a lot of current, millions of amps, down that transformer. And it works like the transformer at the end of the road, where you're taking power off the grid and putting it into your houses. It changes the voltage. And here we use the fuel itself as the secondary winding. So we pass a current through the fuel itself, which induces a magnetic field the short way around the donut. So we now have a magnetic field the long way around the donut, added to a magnetic field the short way around, and that gives you this helix. And that helical field confines the particles very well. So I got one of my students to do a little movie of how these particles are confined. So that blue blob there on the left-hand side is particles entering into the torus, and we're just going to follow them round. And you can see that they move around on this helical path, and they're extremely well trapped. So almost none of them are disappearing. You can even see some, like that one there, going the wrong way round. So they come in this way, and sometimes they bounce back and forth, depending on the magnetic field. But they stay there. They're all staying somewhere inside the torus. So this concept was dreamt up in the 60s. The first one of these existed in the 70s in the Soviet Union. And this worked an order of magnitude or more better than any other concept that we had for doing fusion here on Earth. And since then, more or less, the community has pushed ahead with this type of device. So I'm going to first of all just describe some of the progress that's been made. That I'm sure there's plenty of you in this room who've heard about fusion before, have heard about the promise of fusion before, and have heard the line that fusion is always 30 years away. So I'm going to go back 30 years and see how we've moved forward. So if I go back to the late 70s, to my laboratory, this was a machine that we had in the late 70s. You can see the size of it. So here's some typical men. And you can see this is sitting on a table, basically. It's a very small machine. It was powered by capacitor banks. And when we made one of these stars in the laboratory, it would last for a very, very small fraction of a second. This was the level of data analysis that we used at the time. sort of oscilloscope traces and pencil line markings. I love this particularly. I dug this out of the archives, and the date at the top is my wife's date of birth. And so that really is a generation ago. And where are we now? If we fast forward, this is the machine that we have at my laboratory now. This is, if I was stood in there, there'd be 3 of me, more or less. So it's a lot bigger. And compared to that oscilloscope, very basic digital analysis, we now have really, really cutting-edge tools like this robot on the inside of the machine, completely changed all of the components that you can see in there, which in themselves are beautiful works of engineering. That whole wall, 4 tons of metal, about 60,000 different pieces, was all changed by a robot. So we've moved on tremendously. And we know fusion works. So in that device, in a device called JET, we have done fusion with deuterium and tritium. We've accelerated them together. We've produced fusion power. This blue trace here shows that we had about 16 megawatts of fusion power back in 1997. Now, 16 megawatts is not insignificant. It's 5 or 6 wind turbines. So it's a decent amount of power. Didn't last for very long, of course. The big problem was that for your 16 megawatts, we had to put 25 megawatts in to get the reaction going. And there's not a utility in the world who's going to pay me to do that. However, we understand what the limitation was in terms of the power that's produced, and essentially its size. So we know that if we build a bigger machine, and we're doing that, and I'll talk a bit more about that in a minute, if we build a bigger machine, we can get a lot more power out. So for JET, 25 in, got 16 out. The next generation of reactor that's being built at the moment, 50 in, 500 out. And now, utilities begin to get excited. So, on that path, as we get towards the realization of fusion, I want to talk about some of the challenges. And the challenges are not just physics, they're not just technical, they're also economical. And you can see from fission, known technology, had it for decades, but it was absolute hell to get the financing to build Hinkley Point. In fact, the economics was a bigger challenge than the physics. So I want to talk a little bit about economics as well, because it's really important for nuclear power. But I'm going to start with technical challenges. Let me walk you through what I consider the 5 big challenges ahead of fusion. This is where we want to go to ultimately. We want to have a fusion power plant, a reactor, which is putting, say, a gigawatt electric onto the grid, powering a big town. So first of all, the first big challenge is that on the inside of that reactor, you have to have the fuel about 10 times hotter than the centre of the sun. This is now the inside of JET, the biggest machine in the world that we have at the moment in Oxfordshire. We're now heating that fuel, and inside you have, this is deuterium, racing around that donut. So the deuterium is racing around at extremely high temperatures. Because it's so hot, it will encounter a tritium, and those 2 things will fuse together and produce a neutron and a helium. Now the helium is a lot hotter than the bulk fuel, so it imparts its energy to the bulk fuel, and the whole thing is self-sustaining. The neutron takes 4/5 of the energy, and the neutron is what gives you electricity ultimately. But the neutron also brings challenges. So the neutron will change the properties of the material. So whatever you make the wall from, some sort of solid, those neutrons will pass through that wall, and some of them will displace atoms in the wall. So the wall will change its structure over many years, and depending on how many displacements there are, the properties of that wall, its stress, its ability to handle strain and temperature will change. Now, as well as the neutrons, you also have an incredibly hot heat source there. As I said, 10 times hotter than the centre of the sun. Now, you can't let that heat hit the wall. So what we do is we have a sacrificial point down at the bottom of the machine which takes most of the heat load. You have to worry about how you get the energy out and how you might replace that sacrificial surface. So we've talked about hot plasmas, we've talked about the materials, and we've talked about how you get the heat out. But you need to fuel the reactor, and so for the fuel you need tritium. Tritium has a very short half-life, about 12 years, so you don't find it in nature, you have to breed it yourselves. So we do that by putting a blanket of lithium, this is a liquid blanket, around the outside of the reactor. The neutrons will pass through that lithium, and some of them will produce tritium. So you then have to get that tritium out, freeze it into pellets, and inject it effectively like a machine gun. You're firing pellets into the inside of the vessel. So we know how to do that, and we have done that on small-scale tests. Finally, the last challenge surrounds the availability of the machine. So you can meet all of those challenges, but if the machine only runs for a month a year, the cost of electricity is terrible. So you need to make sure that you can change the tiles as quickly as possible. This is the robot that I talked about in JET, moving inside the vessel, changing the tile, replacing it, and then getting out. You need to be able to do that with a robot. You can't do it with a man. A, it gets quite hot, and B, it takes too long. So you need to be able to do that robotically. So those are my 5 big challenges, and I'm going to talk through what we in the UK are doing to address each of them. But before I do that, let me talk about economics. When I came to fusion, I left school because I wanted to get into fusion a long time ago. And then I went to university because I wanted to get into fusion, and then I did a postdoc because I wanted to get into fusion, and then I got into fusion. And the whole way along that path, I wanted fusion to sort of save the world and take over and replace coal and replace gas. And if fusion was happening now, we'd be doing that, but we're not. And so the raison d'etre for fusion has changed. It's not going to take over the world. It's going to have to be economically competitive and enter into the energy market. So as there's still the drive to replace higher carbon sources, we still have to replace our reliance on gas and coal, ultimately. But you have to, as well as that strategic reason, you also have to be cost competitive. Now, right now, if we look at, this is energy consumption as a function of time, we're looking that fusion is playing about 10% of the energy mix by the end of the century. That sounds dreary and not very ambitious at all. But because the energy consumption of the world is going up, and it will go up significantly, 10% is actually quite a lot. If you compare that 10% to the entire energy consumption in 2020, it's a big number. So we're talking about a terawatt electric, which is a lot, and that works out at about 1,000 power plants. And now, when we're struggling to build one, if you say to me you've got to build 1,000, then I find that quite an ambitious target. It means that from the point of fusion being delivered in about the middle of the century, you then have to grow at 10 or 15% every year for 50 years. No economy's done that, basically. So it's a very ambitious target. Now, fusion's always had this potential, but now it's entering what I call the delivery era, where we're actually going to demonstrate that it works on a commercial scale, 500 megawatts out. This is a machine that's being built in the south of France right now. Actually, this is quite an out-of-date picture. It's many more stories out of the ground. This machine is called ITER, originally the International Thermonuclear Experimental Reactor, now just ITER. And I'll talk a bit more about that as we go through. Lastly, you need to break into the market. So you need to understand what your drivers are for the price of your power plant. If you cost 20 billion, you're going to have the same problems that Hinkley had getting the finance to build it. So what determines the price of the unit? Well, it's effectively 3 things. The cost of the power station, the capital cost in the first place. The fuel is irrelevant, the decommissioning is irrelevant. Really the cost is the buildings in the first place. The power output, so how much fusion power you produce. And that, as a scientist, we love, because that really depends on the plasma physics, the materials, the technology that you use. But actually, the biggest exponent is the availability. And you see this, EDF, if they're down for a day, they go crazy because they're losing £1 million. They absolutely need to be up and running again very quickly. And the availability of a fusion plant will really dictate how economically successful it is. Now, you could question why we care about this now, because we're still in the research and development phase. Why do you care about the economics of the plant you might deliver in 30 or 40 years' time? Well, my contention is that dictates what your research program should look like, and it dictates where you should focus. And our organisation is set up to address that, and I'll talk about that. So what data do we have for how the cost of the plant? So the capital cost is a big factor. On the y-axis here is the capital cost per watt, and on the x-axis is the power output. These are all experimental facilities. None of them are reactors. None of them are putting power on the grid until the power plant at the bottom. But you can see that the trend is good, that the capital cost comes down as you produce bigger and bigger power units. This would say that at a sort of gigawatt scale here, your cost is about $2,000 per watt thermal, which is competitive. Be like fission, quite competitive. But the big problem is ITER. This machine that's being built in the south of France, actually the costs are significantly more than this projection would say. And that's a big issue for the community, because if we're not going to be cost competitive, we'll never break into the market. So why is that? Probably a number of you have heard about ITER. You've probably heard that, ITER is about the same size as Wembley, about 80 metres, 120 metres, 80 metres up. It's about the same amount of steel as Wembley, and like Wembley, it's about twice over budget and twice behind schedule. But there's a good reason for it. It's not just a football stadium. ITER is the biggest science experiment that mankind has ever done, both in terms of price and also in terms of participation. So ITER is a collaboration between 7 partners, the European Union as the host and the biggest contributor, but then also the United States, South Korea, India, Japan, Russia, and China. So you're talking about most of the developed world there. You're also talking about countries who are not natural bedfellows. So you have the Indians working with the Chinese, working with the South Koreans, working with the Russians, working with the Americans. So they're not natural bedfellows. And when the project was set up, they all needed each other, absolutely all needed to do it together to realize a reactor, but they didn't quite trust each other. And so they didn't want to be in a position, and I use this example. This is the magnets, the big magnets, and they're about a third of the price, the total price, and they're a big component. Now, let's say I'm the American government, and when ITER works and we start building reactors, if all the magnets were built by the Russians, I didn't want to be in the position where, to build my reactor, I had to go to the Russians and say, please build me some magnets. I wanted to have the knowledge to do it myself. And so if you're setting up any sort of big engineering project, the way you would do it, there are 18 of these big coils and a spare, so 19. 18 of these big coils, the way you would like to tender for that is to say, go to the market, please build me 18 coils, same spec, on the same test rig, please. That is absolutely not how ITER is designed. So they have to share the intellectual property and the know-how to build that magnet. So what's actually happening, rather than one person doing it, you have the conductor being provided by 6 of the 7 partners. That's then shipped to 2 of the partners to put into cases, which is then shipped somewhere else to be baked, and then shipped to site. Now, that in itself is a bit crazy. But when you look at the fact this is first of a kind and massive, you begin to get an idea of exactly how crazy that is. So, as I said, there are 6 different people providing the superconducting strand. This is one jacketing bench in Florida. It's 800 meters long. That 800-meter bench has to be, precision engineered to less than a centimeter, and it produces miles and miles and miles of superconducting strand. But you don't just have one of these, you've got them all around the world, and each one in itself is a big engineering project. Here's another one in China. And then once you've produced the strand, which is a big deal, about a factor of 10 more superconducting strand than has ever been procured, you then have to wind that onto a very big coil, which is bigger than this stage, and put that into an oven to be baked. Now, that's a big oven. This is an oven which is 48 meters across by 20 meters deep, and it has to heat perfectly isotropically. So this is a big oven. Now, that's a big engineering project in its own right. It takes a long time and a lot of precision engineering to do that. But because this is ITER, you're not doing it once. You're doing it multiple times so that everybody learns. And now you can begin to see why the costs go up. So really the costs, you don't need to worry about the units here or the details, but the costs really lie in the magnets. So the magnets are a really expensive thing, and then the buildings. And to me, as a physicist, that's a bit depressing that, I love doing stuff about heat transport and how we get the heat out and these sort of really interesting techie things. But actually, the buildings are far more important. If you can pour cheap concrete, you'll make the unit price cheaper. Now, understanding the economics and the challenge of how you build a reactor, I think is really important to dictate your research program. And so I want to go through and explain what we as an organisation do to address those 5 challenges that I outlined at the start. Now, our mission, we are a non-departmental research body which sit within UK government. We are here to lead the commercial development of fusion power and all the related technologies that you require for fusion. And very importantly for the UK government at the moment is all about positioning the UK as a leader in that space. And right now we are. We really are maybe the world leader in nuclear fusion. So if you go back decades, that's where we were in fission. We had the first advanced reactor, first commercial reactor, and then we stopped investing, and now we're buying it from the French and the Chinese and the US. Right now, we're a real world leader in fusion. And I'll tell you why, because we can do all of these things that I talked about. Hot plasmas, getting heat out, understanding materials, understanding how to fuel it, and understanding how to maintain it. Now, in terms of the hot plasma, the bit in the middle, we have the best facility in the world. This is a drone fly-through of jet to give you some idea of the scale. You'll see a man in a minute. This is not a small laboratory experiment. There's a man. This is a real big piece of engineering. Jet is the best machine in the world, and it will be the only machine in the world until ITER operates that has the ability to run with tritium, proper fusion fuel, and the ability to run with the same mix of materials on the wall as ITER. And those two things are completely unique in the world. And that means that the UK is very well placed to prepare for ITER and to do the science that's needed. And I give you one sort of tidbit of science. We went through a project in 2011 where we completely changed the wall. So originally the wall was all carbon. It was all, carbon. The beauty of carbon is that it takes a lot of heat. It's really easy to machine. It's pretty cheap. So most machines are built with carbon. The problem with carbon is that it has a very strong affinity for hydrogen. It's why you're all here. It's why I'm here. Hydrocarbons form very easily. And so when you start putting tritium into your reactor, tritium, mildly radioactive, will get sucked up into the wall. And the nuclear regulator is not a big fan of having a lot of nuclear material sitting embedded in the wall. So when we built ITER and when we build reactors, we can't use carbon. So we had to think of a different mix of materials. So we changed the wall, the entire inside of the wall, to being a metal wall with tungsten and beryllium. Now, having done that, we found that changing the boundary conditions really affected your ability to run hot plasmas. So the grey sort of dull circles are what we used to run with our carbon wall, and that's the reason that ITER was designed to be the size that it was, because this is the measured energy stored in the plasma compared to a scaling up to a bigger machine. Then our original experiments were way down here, so we were getting a lot less energy stored in the plasma than we were previously. And so that was a big challenge for us, because all of a sudden we began to worry, oh, maybe ITER won't work. So we have to really understand the physics of that, and it's taken us 3 or 4 years to get back to high stored energies and very hot plasmas. That's not trivial. There's a lot of detailed stuff that goes into that, but the fact that we have JET, and JET is the best place in the world to prepare, the only place that you can do these sort of experiments. And all of it is in preparation for ITER. So I showed you this fly-through of JET. Here's your man compared to that. Here's the same man or woman here compared to ITER. So it's a massive beast. It's a really big engineering project. And ITER will do two main things. One, it will produce 10 times more power out than you put in to get it going. And the second thing is that it will self-sustain. So I talked before about JET, you put 25 megawatts in to get 16 out. So you have to strike a lot of matches and keep it going. With ITER, you'll strike a match, get it hot, and then it'll be like a fire. It'll burn itself. So it'll keep producing the heat to keep the reaction going. As long as you keep throwing wood on it, you don't need to keep striking matches. So you can turn off the heating completely, and it will self-sustain. And that'll be the first time that's ever been done, which is why it's so important and so exciting. Now, you have that incredible heat source. Some of that heat does escape, and it goes against the wall. Now, you have to find a way of exhausting enormous heats. And I use this image of a re-entrant space shuttle because the heat loads are about the same as a re-entrant space shuttle, which is designed to ablate, actually, rather than melt. I show you an infrared image here of the inside of JET. You can see down here at the bottom, it's getting very hot. It gets very hot. In JET, we survive, we don't melt. In ITER, we're right on the cusp, and that's really why ITER is the size it is, because with known technology, that's as far as we could go without melting a bit of the wall. If we were to scale up to a gigawatt electric, sort of Hinkley size, then you're talking about 50 megawatts per square meter, which is like an arc welder, something like that. And that would melt, for sure. And again, coming back to the regulator, not very keen on having a nuclear reactor where the wall is melting. So you need to think of a better way of getting the heat out. Now, we're building a facility to do exactly that. It's a UK facility using UK ideas and built largely by UK companies. What we're doing here, let me describe it. This image that you can see on the right, the bit in the middle is the hot plasma. Now, I don't know if I've got a laser pointer actually, it'd be easier. Yeah, so hot stuff sits here. When it does come out, it moves out radially, and then we sweep it down to a sacrificial surface down at the bottom. This bit here would melt if we ran a reactor using this concept. So what we're doing in this new machine is we've introduced a load of coils down here. You see these extra magnets. And now we'll be able to sweep the power down here. And rather than hitting this wall, we move it out to a wall out here. Now, that in real estate is only about 50 centimeters, doesn't add a lot of space, doesn't add a lot of money and cost. But what it does do is it massively increases the length of time that the particles travel from leaving the hot bit to hitting the cold wall. So because the particles are moving around and around and around and around the donut all the time, as they move down this cross-section, they're actually whizzing around and around the machine. And especially in this box down at the bottom, they're circulating around and around and around before they get to this wall. So this 50 centimeters equates to about 20 meters in actual distance traveled. And that, the whole time they're moving along that 20 meters from here to the door, they're radiating energy, giving away their energy. So when they actually get to the wall, they have a lot less energy. And so our aim is that you take something which sounds ridiculous, 50 megawatts per square meter, definitely wall would melt, and take it down by a factor of 10 to 5. 5 megawatts per square meter would have happened inside your car's engine on your way here. So that would be no problem. This to me is how science should be done. You have a really big problem, you think of a very elegant solution to it, you then do a load of modeling to suggest how you might find that solution, you do a detailed engineering design, then you build an experiment and you test it. And that's what we're doing. And we hope to be running experiments next year. So this machine is a sort of modular build. It looks like a tin can, effectively. It has a lid, top and bottom, and a tin can. This is moving that tin can out of the old neutron shield. Then we cleaned out all of the metal on the inside. We pulled out all the old coils, and then we fit a new cassette. Previously we had 6 coils, now we have 19. So building those coils is a big engineering challenge. This is that cassette being installed. Each of these coils will carry millions of amps, so it has a strong field, and you have coils which are only a few centimeters apart, so they want to rip apart. So just building that is a big engineering challenge. This is then laying all of the armor on the top and craning the bottom, so we have a lid, top and bottom, put the bottom one in first, and then we crane in the main body of the reactor, we crane that back in, put it onto the bottom lid, and then seal those. They need to be extremely high quality vacuum, because you don't want a lot of impurity and gas inside the vessel, so you have to seal that vessel very tightly. Then we crane in all of the coils which sit in this top ring, and finally put the lid back on the top. This is the only machine in the world that will be capable of doing this sort of physics, and because it is so novel and so exciting, Europe, despite Brexit, are just about to invest a significant amount of money into the operation of the device. So when we get going, we hope that we'll be closed up around Christmas, and then we start experiments early in the new year. We want to address 3 main things. The first, and the one that I've talked about the most, is how you get the heat out. Can you get the heat out and really drop the level of heat onto the wall by a significant factor? We will help with ITER. And ITER is still the most important thing in the fusion community, and so we will help with ITER. But the last is a really interesting idea. in that ITER is massive, right? You've seen the pictures of it. It's a very big beast, and it will cost, when it's finished, somewhere between 15 and 20 billion. It's a lot of money. So we're talking about reactors of 20 billion. And we know 20 billion is very hard to finance. So can we drive the size down? Can we make the magnets smaller? The magnets are really where the cost goes. So we're thinking, can you build a reactor which is much more compact? Now you can see just from this geometry that ITER was a sort of conventional ring donut torus. This, you can see that the bit in the middle is very narrow. So instead of looking like a ring donut, it actually looks more like a ball of wool with a hole down, or an apple with a core taken out. So it's almost spherical. It looks round. And by doing that, you make a much more efficient use of the magnetic field. And the magnetic field is what costs. So you can make a much more compact, smaller unit, which is, ergo, a lot cheaper. Now, the big problem with doing that is that you still need the fuel to be 10 times hotter than the center of the sun. But you're putting it into a much smaller vessel. So the chance of you melting the vessel is a lot higher. So you need a really clever way of getting heat out. And that's what we're doing with this test of putting all these coils down at the bottom. Can we exhaust a much higher level of heat? If we can, I think this is a real game changer for fusion, in that all of a sudden you can start building reactors which are much smaller. We try and explain that a little bit more. This is a tube, a magnetic tube. When the particles leave at the middle, they leave from the hot bit and they get swept down into this exhaust system at the bottom. They'll follow a tube. So they move down effectively a hose pipe. The area of that hose pipe, the width of it, is dependent on the magnetic field. Now, roughly speaking, the magnetic field decreases as you move away from the middle. So it decreases as you move away, and the area of the hose pipe gets bigger. So you spread the heat over a bigger area. So let me show you a little movie of particles they leave in the middle at the top, they come down, and they'll hit the plate. And this is looking at the width of that hose pipe, of that magnetic tube that takes them down to the wall at the bottom. And you can see in the 3 dimensions, it doesn't really change. It stays more or less the same width, same size. If we compare that with our new exhaust system, so you can see how big it is at the top. It comes down, follows the same sort of path, but now we're going into this extra 50 centimeters. And all of a sudden, the tube is getting much bigger, the diameter is getting much bigger, you're spreading the heat over a much bigger area. So now, when the particles and the heat get to the wall, they're spread over a much bigger area. And we hope that this really drops the heat which hits the wall. In fact, we've done some detailed calculations of this. In our original machine was the green line, so pretty high heat flux. Then as we run with our new machine, it'll come down to the black line. And then we energize all of these coils and sweep the heat out into the furthest region possible. It comes down to the blue or the red. Well, you can't even see it on the same scale. So there's a factor of 15 lower heat flux. If that happens, I really think it'll be a massive step for fusion. Let me move on to the next challenge. We talked about hot plasmas. We've talked about how we get the heat out. We also need to understand how the neutrons affect the wall. Now, in terms of our ability to handle irradiated materials in this country, universities like Lancaster can take very low activation material because they're in the middle of a town. They can't take very radioactive stuff. Right at the other end, down the road, we've got Sellafield where you can take whatever you like, uranium, plutonium, and certainly irradiated material. We sit more or less in the middle of that space. So we can take some slightly hot stuff, hotter than you could take in a city centre in a university, but not uranium, not plutonium. We're not a licensed site. So we now have a new materials research facility where we will take in structural stuff, steels and tungsten, things like that, that's been put into test reactors to look at how the neutrons affect materials. So we take it through this series of hot cells. We'll take in a bit of steel, which is about the length of your finger. We'll chop it up, polish it, prepare it for testing, and it'll come out about the size of your fingernail. And then that can either be tested at our site with our instruments, or it can go off to our university friends. I'll show you one of the types of tests that we do. It costs a lot to get a finger of irradiated steel, so you want to do lots of tests with it. So you want to do it on a small scale. This is on the tip of a pin, on the pointed end of a pin, and I'll show you a zoom out of that in a minute. We're cutting away, effectively this is like a sandblaster, so it's a beam of gallium ions, which is just like sandblasting something away. So it cuts away the material, and you'll end up seeing a cantilever, and this is, as I say, right on the tip of the pin, so you can't even see it on this scale. Then you can test the properties of that material, so you can put a strain on it and see how it bends, how it's affected by a force. You can look at cutting it, welding it, so here we're electron beam welding it and look at how good the weld is, and this is all on a scale which is finer than a human hair. So it's an incredibly high resolution micro sampling and testing. Now I'll move to technology. So let's say we understand the materials and we've got a material which can take the neutrons. Then you have to build it. You have to find a way of manufacturing it. So I'm going to give you one example of the sort of design work that you have to do. We're going to look down at the bottom in this area that takes a lot of heat and look at how we might design one of the tiles. There will be millions of these tiles. Let's look at one of them. So the problem is that you have a block of tungsten. Tungsten takes a lot of heat before it melts. And you're putting heat flux in a sort of cyclic way. So it's not constant, it's fluctuating, the level of heat that's going onto it. You need to cool that block. If you just leave that, it will melt. So you need to actively cool it. Now you can do that by putting a pipe in the middle of the block and passing some sort of coolant through it. That in principle is fine, but the pipe and the armour are made from different materials, and so they expand at different rates, and that puts a stress on that joint. So you need to think about how you join the pipe to the armour. Now, we go through a design process which actually is not from fusion, it's borrowed from aerospace, where they have similar deals inside of engines, and we find an optimum design. And then we have to try and manufacture it. Now, the first thing that we used to manufacture was this sort of tungsten foam, and then we used a felt metal. Neither of those worked very well. So we ended up 3D printing it with these tiny little fins inside the gap between the pipe and the armour. So this was done with a 3D printer. We then took an X-ray, a tomograph of that join, and you can look at the quality of the braze, and actually that red bit, you don't really need to understand it, but the red bit there indicates an imperfection in the join. Now normally, we would say, is that good enough? Don't really know. And so we just put it into a test facility and put it under a lot of heat. Now, that is expensive and takes a lot of time. So instead, we did a virtual prototype. On the left is the as-built, on the right is as-designed. The colour is the stress. Now you can see the as-designed has a sort of isotropic stress everywhere. The as-built, where the braze is not very good, has a big fluctuation in the stress. Now that in itself is probably tolerable. The big problem comes, you might not be able to see it from the back, but the armour is actually moving up and down by a few millimetres. And the fact that the armour is moving means it would melt, because it would get a lot of heat on that corner, which lifts up. All the heat would hit the corner and it would melt. So we know that this wouldn't work, so we didn't bother testing it. So instead, we revised the manufacturing process, came up with a better way of doing it, and then went through that X-ray and then an ultrasound. The ultrasound was very good, so then we put it into a high heat flux facility where we put a cycle of very extreme heat flux onto it, and it worked brilliantly. And it lasted for actually 150 cycles at 20 megawatts per square metre and worked beautifully. This whole loop, which is just for one small component, took about 2 years. So it shows you the level of really detailed high-tech engineering you have to do. I'm not going to talk much about tritium. To operate a fusion reactor, you absolutely need tritium. It's one of the fuels you need. JET in Oxford is the only place where we have a complete closed tritium loop, where we know how to store tritium, inject it in, get it out, and at end of life, get tritium out of the water or out of the wall. We actually have built 2 new detritiation facilities where we can get tritium out of water and tritium out of materials, solid materials. There's nowhere else in the world, other than places who build weapons, where you can do this sort of stuff. And finally, I turn to robotics. As I said, you really must make sure that you can get in and fix things as quickly as possible. This is the robot that we have on the inside of JET. I showed you this before, where we completely changed the wall. That was 4 tons of metal. These are all very delicate components. We have 2 of these. One arm comes in one side, one arm comes the other side. I'd say that this is like the surgeon and the wet nurse, that you've got one holding all the tools and the other one doing the operations. This guy is sat 50 feet away from the robot, so he's nowhere near the machine, but what he does on his arms is what the robot does. It's so delicate that he can feel what's actually happening in situ. So if he's torsioning a bolt or screwing something, he can feel when it's at biting point. He knows how much more torsion to apply. So you have these haptic arms, this force feedback, and we've been doing this for 20 years now. And on the back of this expertise, we've just opened a new centre, which is for these sort of applications, robotic applications, anywhere where you don't want to put a man. And there's lots of places where you don't want to put a man. Nuclear is obviously one of them, but also in space, in decommissioning bits of Sellafield, in petrochem industry where you're at risk of explosion. You can put a robot in there. That technology is moving on apace and is being driven by nuclear. You will have seen, all of you will have seen driverless cars driving around Milton Keynes or roads of London. The sensors which sit on the front of that autonomous vehicle, the sensors on the control system used to drive that car, also sit on the robot that moves inside Jet. Exactly the same. Software, control system, sensors, exactly the same. So there's enormous overlap in fields where you don't necessarily think of big overlap. And because of this expertise, UK industry is delivering all of the robots for ITER. So this is one of the robots which changes the tiles at the bottom, one which changes the heating systems, ones which change the diagnostics which fit the machine. About £200 million worth of contracts coming in into the UK supply chain. And that allows me to touch on the role of industry. So far I've only really talked about what we do as a national lab, but we are incredibly well coupled to both academia but also to UK industry. My organisation is about 1,300 people. We're definitely not big enough to be designing and building reactors. We know that. And we don't have all the skills that are required, the sort of big, heavy engineering skills that are required. So we are working with the supply chain, which I think is mutually beneficial, really, in that we can upskill in the very high-tech stuff that we do know about, but the supply chain can do all the heavy lifting and have the capacity and the capability to deliver very big components. That gives us critical mass in terms of skills and people, and it means that we can benefit from the nuclear industry in this country, which is exceptionally good. So in decommissioning and in regulation and in enrichment and various other things, we are exceptionally good in this country still. And so we have about 65,000, 70,000 different nuclear professionals, which is a big supply chain. And so we're bringing that to fusion as an application as well. And ITER has been instrumental in this. I put this slide together to try to begin to show some of our collaborations, and I did it in 2 minutes and ran out of space and gave up. But it's ever growing, and we as a national lab are connecting these companies out to opportunities, notably for ITER. So I started by talking about some of the challenges of economics, and I said that there are three main things which drive the price. The first is the cost of the power station, the second is the output power, and the third is how much of the time you can run the reactor. So what are we doing to address those three big challenges? Well, I start with the cost. The whole idea of this compact, small machine that we're building is, can you build a smaller reactor and not melt the walls? And if you can build a much cheaper unit price. And that will be, we'll start running experiments next year, and it will be really exciting for the community. The second area is about power output. Can you make sure that ITER gets 500 megawatts out? Can you make sure it reaches those goals? And JET is the best place to do that. And the third is on availability. And availability we're looking at from two angles. One, the robots to get in and fix things. And two, developing the materials and the joint techniques and other things, which will mean that those components last for longer. So we're directly trying to address the things which affect the economics. So as an organisation, as a national lab, we see that as a very important part of our DNA, as part of our raison d'etre, is to do an R&D programme, but which is framed in the real world, is framed in the route to commercialisation. I hope I've shown you some of the unique things that we can do in this country, which address all of the major issues. So I had a little movie which described the 5 big things, and we can touch on all of them. Now, probably there'll be some questions about Brexit. I think it's really important that the UK doesn't turn its back on the international community. Fusion it's a wonderful thing to be involved in that when we started fusion research in the 50s, it was classified, and there was basically the Soviets, the UK, and the US all working independently of one another. So we've gone from that extreme to now, I would contend, being the most collaborative of any science discipline, where we are completely dependent on our international partners and we work as a team. I think it's vital that the UK stays in that international arena and wants to reach out and play a leading role in that community. And with that, I will thank you very much for your attention.